Alright, let's try this electronic lecture thing. So hopefully you're watching this before the review session. This material will be on the exam, so watch it. If you have questions, ask. Hopefully you can see everything, hopefully you can hear everything. Seems to be working okay from my end, so we'll see how it goes. So what we're going to do is we're going to finish the examples from the Chapter 9 notes. We'll get through whatever we can. Then we'll go through a short handout about how to analyze raw data. Some of the MyStatLab problems provide you with just the data. So what do? Well, it's pretty simple, and we'll go over that. So we're talking about hypothesis tests for proportions. We did example 3 on Thursday, so we'll begin with example 4. So in this example, it says, suppose that in the past, 40% of all adults favored capital punishment. So right away, this is starting to look like a proportions problem because we're given percentages. Okay. This first bit of information, this is sort of a historical value. This is something we sort of already know. So this is telling us that we think that P, which in this case represents the proportion of all adults favoring capital punishment, is 40%. So what we want to know is, do we have reason to believe that the proportion of adults favoring capital punishment today has increased? So this is telling us sort of what the claim is, or what we want to show. So has that proportion increased? Has it gotten larger? Is it now bigger than 40%? The way that we'll evaluate these hypotheses, as we'll see, or these claims, is we have a random sample of 15 adults, so that's N, sample size, and 8 of them favor capital punishment. And we want to use a 5% level of significance. So, as I mentioned before, whenever you see level of significance, that's telling you that you need to do a hypothesis test. If I want you to create a confidence interval, I'll give you the confidence level. If you are doing these problems on your own in your career, you would choose either to do a hypothesis test or a confidence interval, and you would choose your level of significance or your confidence level. For now, I will provide those to you. So the null hypothesis, that's going to be the P equals 0.4. The null is always the one with the equals. That's what we will assume is true as we analyze the data, and we'll see how or if they agree. The alternative hypothesis, HA, that's going to be the P larger than 0.4. So if we look at our data, 8 out of 15, I don't know what that is by just thinking about it, a little more than 50%, 53%. So that's our P hat. So it does seem like it's gone up. Okay, we're sort of already agreeing with the alternative hypothesis. Our evidence is that 53% of adults favor capital punishment today, so that's agreeing with the alternative. But we can't just stop there. This is only a sample of 15, which, for the purposes of this problem, we have to assume that this is large enough. Is it actually large enough? Don't know. Okay, the rule of thumb said 30, but it also said that N times P needed to be bigger than 5. So that, in this case, is about 7 or 8. So by some rules, we're okay. So we'll just go ahead and assume that this is a large enough random sample. This is 1 P hat. If we had done this again, went out and got another sample of 15, we'd get a different P hat. So we need to account for that variability. So that's what's built into this hypothesis test. That's what's built into the p-value. So to analyze these data, since we're doing a hypothesis test with proportions, we're going to use one prop z test. So we go to the calculator, stat tests, one prop z test is number 5. Okay. We believe that the value is 0.4. That's from the null hypothesis. We observed 8 successes. Oops. out of 15 that we sampled. And we think that the proportion has increased. Okay, so then we can calculate that. So what we find, or what's given to us, we have a test statistic z of 1.05. So what that means is if the null hypothesis were true, if the true proportion of adults favoring capital punishment was 40%, then what we've observed, the 53%, or 8 out of 15, is only one standard deviation above the mean. So it's not too far away from what we would expect, which is 40%. The p-value, that's what we'll ultimately use to make our decision, is 0.1459. So again, what that means is if the null hypothesis were true, so if we expect to see 40% of people or 40% of adults favor capital punishment, then there's about a 15% chance that we would see our data or something more extreme. In this case, there's a 15% chance that we would see 8 out of 15 or more favoring capital punishment. So a 15% chance to see what we've seen, that's not very small. Okay, that's pretty likely. So what's happening now is our data seem to agree with the null hypothesis. We expected 40%, we got 53. Statistically, those are close together. They're one standard deviation apart. So we're not seeing anything unusual, so we don't have any reason to support the alternative hypothesis. Okay, so the way that we've sort of formalized that conclusion, we note our p-value, which was 0.1459. And again, you can also express these as percentages. Sometimes it's easier to compare the p-value to alpha. We always compare the p-value to the level of significance. So in this case, 0.05, or equivalently 5%. So what we see is the p-value is bigger than alpha. When the p-value is large, then that tells us that our data, what we've observed, is not unusual. If our data are not unusual, that means that we do not reject the null hypothesis. It seems okay. And if we don't reject the null hypothesis, that means that we do not support the alternative hypothesis. Okay, so we need to take the do not support HA and rewrite that in terms of the problem. So the conclusion for this example would look something like at the 5% level, the data do not support HA, which we have to write in terms of the problem. The data do not support that P is larger than 0.4, so the data do not support that. The proportion of all adults today who favor capital punishment has increased. Okay, so that's a perfectly fine conclusion. That's what was asked in the question. Has that proportion increased? And we're saying no, at the 5% level. Basically, there's a 5% chance that we could be making the wrong decision. It's sort of related to the confidence interval. So if we're 95% confident that we've captured the parameter, then that means we're 5% confident, I suppose you could say, that we've missed it. So in this case, the level of significance, which we'll get to in a little bit, is also the probability that we make a wrong decision. So there's a 5% chance that we're making the wrong decision, but our decision is the data don't support that the proportion's increased. We have no evidence, no strong enough evidence to say that it's not 40%. So example 5, similar. A fuel, I think we've seen this one with a confidence interval also. A fuel oil company claims that 1/5 of homes in a certain city are heated by oil. So we see the claim. Sometimes in the problems it'll be worded where the claim is an equivalence. So they're saying that the proportion of homes heated by oil is 1/5. So whether it says claim or not, anytime there's an equivalence, that's going to be the null hypothesis. So that's 0.2 or 1/5. They're both the same. Okay. Generally, claims are the alternative hypothesis, but you have to read into the context of the problem. This is stating a specific value, an equals, and that's going to be the null. So do we have reason to believe that less than 1/5 of homes are heated by oil? So P, that's representing the proportion of homes in this city, this certain city, that are heated by oil, and we're going to try to show that that is less than 1/5, which is 0.2 again. So the way that we'll evaluate those two hypotheses is that we have a random sample of 1,000. That's certainly a large enough random sample, and we find that 136 are heated by oil. So from those two pieces, we can create our p hat, so our observed sample proportion. So that's 136 out of 1,000, which is 0.136. Okay, so again, we look at our data, what we've observed, and it seems to be agreeing with the less than 0.2. Okay. That less than 0.2, that's going to be the alternative hypothesis. The equals 0.2, that's the null hypothesis. So our data, our evidence is seeming to support the alternative hypothesis. Will we ultimately end up doing so, supporting the alternative? We don't know. The only way we don't know yet, I guess. We'll know which one to support after we get the p-value. Okay. So the last piece, we have the alpha is 1%. So that's telling us that we're doing a hypothesis test. So again, we'll use the function 1 prop z test, and we need our p-value. So we go to stat tests, 1 prop z test. Now we think that the proportion is equal to 1/5. So you can type in 1/5, 1 divided by 5, and press enter, and that will change it to 0.2. So if you didn't know it was already 0.2, that's fine. You can enter an equation there. We observed 136 homes heated by oil out of a random sample of 1,000. And we're trying to show that less than 1/5 are heated by oil. So we select, it's hard to use the calculator and the camera. Less than 1/5, so then we can calculate. So here's what we get. So our test statistic, the z, is -5. So again, the interpretation of the test statistic, that's telling you how unusual are your data if the null hypothesis were true. So in this case, if 1/5 of homes were heated by oil, then observing 13% heated by oil, well, that's 5 standard deviations below what we would expect. So 13% is 5 standard deviations below 0.2. That's quite different. So what we've observed is not what we expect. They're pretty different. The p-value, you have to read carefully in this case. So it says 2.1. However, a p-value is a probability, so it can't be 2.1. So at the end we have that e to the -7. We need that, so don't ignore the e -7. So 2.1 e -7, So what that is equivalent to, you can move the decimal to the left 7 spots, which means we're going to have 6 zeros in front of the 221. So 0.6021. So a pretty small p-value. So the interpretation of that again is sort of what's the probability that you would see these data or something more unusual if the null hypothesis were true. So if 20% of homes are heated by oil in this certain city, then there's a 0.0000021 chance that we would see 13% heated by oil or fewer. So not very likely. So rather than believing that we've observed something